Okay, in this video we're going to look at the third installment of Riemann sums, and in the first two videos we looked at a lower Riemann sum using 5 rectangles, and that's this picture right here, and you can see that that fifth rectangle actually disappears, and it's pretty evident that this is underestimating the area that's bounded by this curve, the x-axis and the y-axis. It's underestimating. The upper sum is clearly overestimating using the same number of rectangles. Okay, if you watch the previous two videos, we got an upper sum. We got an upper sum of, I believe it was, what the heck was it? It was oh goodness, I want to say it was 19 over 25. And the lower sum was 14 over 25. Okay, so the upper sum you can see is just slightly bigger than the lower sum. Now we want to know what's the actual area under the curve, and you can get a visual of this by, I don't know if you can see this in the video or not, but that says n equals 5, and now I'm going to animate those increments, and you can see that those rectangles now, at least the width of them, are getting smaller and smaller and smaller. And the smaller the widths get, the closer these rectangles actually approximate the area that I'm interested in. Now it turns out, I'm going to stop that animation now, it turns out it doesn't matter if I use a lower sum or an upper sum to do this. If I let the number of rectangles go to infinity, then it's going to do a very good job of not just estimating the area, but actually calculating the real area that's underneath this curve. Now we can actually drag this to the end point here at 1, and you can see these rectangles filling up the space nicely. Well, how do we do that? Well, I'm assuming you've seen the previous two videos, and I'm going to make some leaps here. I'm going to assume that you know how to calculate the width now of a rectangle, and by now hopefully you would know to take the interval, which in our case is 1, and divide it by the number of rectangles you want. Well, we want an infinite number of rectangles, and we're actually going to just call the number of rectangles n, and you can imagine that we're going to use our limit process to let this n blow up to infinity. Well, what is the height now? What is the height of one of these rectangles? Well, the height of one of these rectangles, let's go back to the animation here. Well, I can see that. Okay, let me plug in 5. Let's get us back to 5 rectangles. There we go. Well, in this particular drawing, the lower sum is giving us a right endpoint, and if you watch the previous video, right endpoints are nice. Right endpoints make for very nice heights of rectangles. The upper sum, let me get this back to 5. The upper sum, we actually used a left endpoint, and left endpoints, they're not too difficult, but they complicate things a little bit. You have to deal with I-1s, or you have to change your sigma notation to start from 0, and it can cause some problems if you're not used to doing that. So I elect to use right endpoints whenever I can. Now, just to make this point, a right endpoint does not always give you a lower sum. A right endpoint could give you an upper sum as well. If I change that to a plus, then now you can see the lower sum. This is still a lower sum, but now it's a left endpoint. Okay, it's no longer a right endpoint. So I would probably default to the upper sum in this picture right here. Let's go ahead and change this back to what it should be. And here we go, back to our right endpoint rectangles that estimate our area. Okay, so the right endpoint, the height of this thing right here is simply going to be the width of my rectangle, f of the width of my rectangle. So whatever rectangle I want, if I want the height of the second rectangle, I would take 2 times my width and then throw that through my function, and that would be the height. Okay, so the height then is going to be f of the width of my rectangle, and we're going to index it by I. Okay, where I is simply taking on integers. So if I want the height of my first rectangle, I would be 1, and that would be f of 1 over n. If I want the height of my second rectangle, let I be 2, and I get f of 1 over n times 2, which would put me right here. Okay, so let's go ahead and write our series now. And our series this time is going to go from 1 to n. Okay, and the height. Well, what is the function? The function is 1 minus x squared. And to get a little bit more explicit expression now for our height, I'm going to just take this input and I'm going to substitute it right here in for x. And I should get the following. I should get 1 minus my input squared. Now this right here is my height. Okay, this is my height. And that height, remember, I need to plug in 1 over n times I. So this represents the height of my rectangle. Okay, multiplied by the width of my rectangle, which is 1 over n. Okay, so this right here is my width. Okay, so like the previous videos, I'm not going to bore you with all of the algebra here. I'm going to skip some steps and jump ahead to what this actually equals. Okay, so if you crunch the numbers or the letters or whatever it is you're crunching, then we should get the following. We should get 1 over n minus 1 over n cubed. That's a 3 right there. Sorry. I to the second power. Okay, so that's my series right there. Okay, so if this is my series, think about what I want to let n do. What I really want to let n do is I want to let n go to infinity. So I'm actually going to take the limit. I'm going to take the limit of this series as n goes to infinity. Well, let's go ahead and do that. And again, I'm going to skip some steps here, hoping that you can do the arithmetic and the algebra on your own. I'm going to simplify this series to the following. I'm going to break it up from I to 1 to n of 1 over n. Now remember, n is just a constant. It's not a constant. It's a number. We're letting this number go to infinity. Okay, minus. Now, if n is a number, then that means 1 over n cubed. You can think of that as a constant, and that would be 1 over n cubed. I pull that guy out, and we go from 1 to n of I squared. Okay, there it is. All right, going a little bit further with this, we have. Well, how do you sum this? How do you sum? Now remember, you could think of this as a constant. So how do you sum a constant going from 1 to n? Well, you multiply. So n times 1 over n is just 1 minus. And by now, I would hope that you recognize this formula right here. The formula for let me just outline this. There's a formula for this, and hopefully you recognize it as n times n plus 1 times 2n plus 1 all over 6. Okay, that's what this thing equals. If we multiply it by 1 over n cubed, we should get the following. We should get 2n cubed plus 3n squared plus n all over 6n cubed. Now, combining these two things together, if I find a common denominator here and combine these two, I get the following. I get the limit as n goes to infinity of 4n cubed minus 3n squared minus n, and this is all over 6n cubed. Okay, all that is left to do is to take the limit of this thing right here. And what you can do, maybe some of you see what the limit is right away, but the way we do this is you look for the highest power on n and you divide every term by it. So let's do this real quickly. Doesn't take too long. As n goes to infinity, now 4n cubed divided by n cubed is just 4 minus 3 over n minus 1 over n squared. All I did was I divided every term by n cubed. And whatever we do to the numerator, we also have to do to the denominator. Okay, now let n blow up. Let n get really, really big. Well, what would this limit be? Well, the limit of 4 as n goes to infinity is just 4. The limit of this as n goes to infinity is, I guess that wouldn't be plus, it would be minus 0. The last one would be minus 0. And downstairs I get 6 for an overall area of 2/3. Now if you check, 2/3 is actually less than 19 over 25, which was our upper sum from one of the previous videos, and the lower sum, if you remember, was 14/25. Okay, and 2/3 happens to live in between these two guys right here. 2/3 is the actual area under the curve. It's not an estimation. It's not an approximation. That is the area. I hope that made sense, and we'll see you in the next video.